A black hole is not a cosmic vacuum cleaner. It is a place where gravity has become so intense that past a boundary called the event horizon, no known signal can escape back to the wider universe. Not light, not radio waves, not a message from a spacecraft. That sounds like science fiction, but the basic idea comes from Einstein's theory of gravity. If enough mass is squeezed into a small enough region, space and time curve so sharply that every possible path inward leads deeper in. The event horizon is the point of no return. It is not a solid surface. You would not hit a wall there. It is more like crossing an invisible waterfall in space-time. Outside it, escape is possible. Inside it, all futures point toward the center. Scientists do not think black holes roam around swallowing everything nearby. Far from them, their gravity behaves like the gravity of any object with the same mass. If the sun were somehow replaced by a black hole of equal mass, Earth would not be sucked in. It would keep orbiting. Though without sunlight, life would not survive. What makes black holes extraordinary is not that they are magical. It is that they take ordinary physics to an extreme. We have strong evidence for them from stars orbiting invisible massive objects, hot gas glowing before it falls in, and gravitational waves from collisions between compact objects. But the inside remains hidden. The event horizon protects whatever happens beyond it, from direct observation. So the first lesson is simple. A black hole is not a monster. It is a region of space-time where escape ends and where our best tested ideas meet their most extreme test. And that boundary leads to the next mystery. If no light escapes, how do we know black holes are there at all? Black holes are famous for being dark, but many are found because their neighborhoods are brilliant. When gas dust or even a star gets pulled into a tight orbit around a black hole, it can form a furious disk. The material rubs, compresses, and heats up before it crosses the event horizon. That last glow can be brighter than entire regions of a galaxy. This is one reason black holes feel so paradoxical. The object itself emits no light from inside the horizon, but the space around it can become one of the universe's most powerful lamps. Gravity also bends light. Near a black hole, space-time is curved so strongly that light from background stars and galaxies can be stretched, warped, or redirected. Astronomers call this gravitational lensing. It is not a trick of glass. It is space itself changing the path that light can take. There are other clues. Stars can whip around something invisible at astonishing speeds. Hot gas can flicker as it spirals inward. When two black holes collide, they can shake space-time and send gravitational waves across the cosmos. None of these clues requires us to touch the black hole. They reveal it by its influence. Still, scientists are careful. A bright disk or strange orbit must be studied with many observations before a black hole is the best explanation. Space contains neutron stars, dense star clusters, and other compact objects that can sometimes imitate parts of the story. That is what makes black holes so captivating. They are hidden objects that announce themselves through motion, heat, warped light, and ripples in space-time. The takeaway is that darkness in astronomy is not emptiness. Sometimes it is the outline of something powerful enough to shape everything around it. And once we know they are real, the harder question begins. What happens to information at the edge of no return? The deepest black hole mystery is not just what falls in. It is what the universe is allowed to remember. In ordinary life, information is hard to destroy completely. Burn a book and the words vanish for us. But the ashes, smoke, heat, and light still carry traces of what happened. Physics usually assumes that the past is not erased from the universe in a total way. Black holes challenge that idea. Anything crossing the event horizon appears lost to outside observers. At the same time, black holes are expected to give off a faint quantum effect called Hawking radiation. Over unimaginable timescales, this radiation suggests a black hole could slowly shrink. Here is the puzzle. If a black hole eventually fades away, what happens to the information about everything that fell inside it? Scientists call this the black hole information problem. It is not a settled mystery. Many ideas exist. Some suggest information is somehow encoded near the horizon. Some point toward deep links between gravity, quantum physics, and the fabric of space itself. Others explore whether our description of the inside is incomplete. What is known is that black holes force two great theories to meet. General relativity describes gravity and spacetime on huge scales. Quantum physics describes matter and energy at the smallest scales. Both work astonishingly well in their own domains, but near a black hole's deepest boundary, we do not yet have one complete picture. That uncertainty is not a weakness. It is a map of where science is still growing. Black holes matter because they are not only objects in space, they are questions made physical. They ask what time is what information is, and whether the universe keeps a perfect record of itself. The memorable takeaway is this: a black hole marks the place where escape ends, but understanding begins. And somewhere beyond that silent edge, the next great theory may be waiting.